So it's a pleasure to welcome Rob Phillips for the fourth and last time. He will give today a lecture on the power of field theory to bear on problems in biology. And so his title of his talk is beginning with a geometric argument, triangles, and we'll go from this to continuing description in physics and how they impact on the understanding of biological processes. Let me thank Rob before he starts for his being with us during the month of May. It has been really lovely, and thank you all for participating to his lectures. Thank you, Rob.
Thanks. I don't need that. All right, good afternoon, everybody, and thank you so much for being here. It's been really a huge both privilege and pleasure to be here. So, as many of you will know, I've basically had a variety of themes that I wanted to cover in this course, this mini course. And today I want to tackle another one of the topics that I am very, very enthusiastic about, and that is the world as a continuum. And I'll explain what I mean by that. Before I go on, I need to say that this is really something that's a joint effort with Christina Hishen, shown here. She and I have recently written a book on active matter together called The Restless Cell, which will come out next year, and we usually give this talk together. So I have basically three topics. So I'm going to start out with the perhaps absurd sounding comment or question, are there even atoms? And then I'll talk about the continuum theory, and then I'm going to reserve the last 15 minutes for sort of higher level comments about why I think a course like this could be of interest. So that's what I have in mind. So are there atoms? So I want to just start out with, I guess, in a way, to try to challenge the idea that mechanism in biology is intrinsically something about molecules. And what I mean by that, last week I was in the Azores, got to see some amazing whales. And one of the things about whales that's very interesting is they can spend a lot of time underwater, as many of you know, sometimes as long as 2 hours. Their myoglobin and their hemoglobin is different than ours. And it's very cool and interesting to know their structure. But, you know, when pushed, I guess when people try to tell me, oh, it's evident, it's self-evident that the way we need to talk about biology is through the picture of molecules, I always tell them, yeah, I don't really take you seriously because you didn't mention the quarks. Everybody knows that, you know, molecules are made of atoms, but everyone knows that atoms are made of nuclei, and everyone knows that nuclei are made of quarks, and you didn't mention them in your description. So clearly, there's something wrong with your picture of the world. I mean, it's no different for somebody that's enchanted with molecules to tell me, oh, but you're working at a higher level and you didn't mention the molecules. So I think this is a very important theme. And what I'm going to say today is, in some sense, kind of in line with and even in some sense inspired by this really wonderful 1972 article by Philip Anderson. In fact, this is the 50th year anniversary of this great article, More is Different. I'm going to write a little commentary about it because I think it has a lot to say, not only to biology or to physics, but also to biology. This was written by him at a time when he was challenging the worldview that somehow particle physics should be the dominant paradigm for how we think about what's important in physics. He didn't buy that. And his argument was that there are lots of examples where you are looking at some phenomenon and it would be ludicrous, frankly, to talk about the Golden Gate Bridge in terms of atoms. I don't know anybody that would ever do that, ever, really. And similarly, if you look at this picture over here, it's one of my favorites, actually. I sailed right past here. This is, Cedros Islands off the coast of Baja, and there's amazing, beautiful vortices being shed off of the island by the wind direction. So, I think, it's very interesting as we look at a beautiful phenomenon like this. I think I showed this maybe at the beginning of the course. If I didn't, I should have. It's really one of my all-time favorite videos, and it makes me think very much of, in the 1890s, Heinrich Hertz. What he did is he actually worked out the theory of what we call indentation. So in other words, he figured out what happens if you push on a material. He solved that using elasticity theory. But if I interest myself in the indentation of this collection of fish, which are active, I'm going to make the assertion, I'm not sure that Jean-François is going to believe me or agree with me, but I'm going to make it anyway. I don't think we currently know how to solve the problem of indentation of an active material, especially this one. I mean, I've tried to do some experiments on this. So what I want to do is, with that as my background, very brief, I just want to challenge this idea of molecular mechanism with a different worldview, and that's viewing the world as a continuum. So let me say what I mean by that. So actually, all of us are quite used to this idea of a continuum. And here, I'm showing you a weather map that shows us both it shows the velocity of the air. And I want to call your attention to these two amazing quotes from first Einstein and Infeld. They wrote this beautiful book called The Evolution of Physics, very worth reading. And in it, they say a new concept appears in physics, the most important invention since Newton's time, the field. I just truly believe in my heart of hearts that is not hyperbole. I think Einstein completely meant that when he said those words. Feynman said, from a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. So what is this idea of the continuum? So I like to think, just for example, of a pipette, which I'm showing you in the upper left. A pipette which is going to release chemoattractant, molecules that bacteria are attracted to. And the point is that, of course, we know that those molecules are discrete entities, but in fact, we find it very convenient to eliminate that actual knowledge and replace it with a fiction. And the fiction is the idea of a continuous field of concentration, where at every point in space, the claim is that there's a certain number of molecules per little tiny volume of a tiny box. And these ideas are powerful across a huge range of scales. So today, I'm going to illustrate them over about a billion-fold difference in scales, ranging from wildebeest herds all the way down to actin filaments in a very small parasite. So, just to continue hammering home this point, this is for those of you that have any sort of physics background, this is really a great article by Freeman Dyson. It's only 6 pages long. And I just want to give you a few quotes from it to contemplate. So he says, in a way, the same thing that Feynman said. We, with the advantage of hindsight, can see clearly that Maxwell's paper was the most important event of the 19th century in the history of the physical sciences. The ultimate importance of Maxwell's theory is far greater than its immediate achievement in explaining and unifying the phenomena of electricity and magnetism. Its ultimate importance is to be the prototype for all the great triumphs of 20th century physics. And then here he says, and we may hope that a deep understanding of Maxwell's theory will help to lead the way toward further triumphs of physics in the 21st century. And I guess I would just say, I'm advocating for this idea of field theories of matter, if you'll let me say it that way. So what do I mean by that? So, when we think about the ocean, one of my favorite things of all to think about is the ocean. I know it's made of molecules, but I certainly don't have any experience of molecules when I go swimming at all. I feel cold. I might feel my ears popping if I go deeper in the water, but there's no experience of molecules. And so the notion here is that at every point in the water, I can ascribe to it a density, I can ascribe to it a velocity, I can ascribe to it a temperature, and that's true at every point in space. Similarly for the atmosphere. Now, what are the conditions under which I'm licensed to make that kind of an approximation? I'll state it simply that I think it's more subtle than what I'm getting ready to tell you. So the idea is that I discretize the system. I imagine the system is built up of a bunch of little blocks, and each one of these blocks has a length scale, a width, delta x, which is big compared to the size of molecules. So if I'm thinking about the atmosphere, maybe I'll take cubes, which are of dimension 1 centimeter, or I could take 1 meter even. The second point is that the variation in the field, for example, the variation in the density, this watch that I'm wearing has about 5 meter resolution. When I ride my bike or I go climb a mountain, it basically changes in 5 meter increments. And it even tells me my rate of ascent. So it's basically measuring the pressure, and what I'm saying is on the 5 or 10 meter scale, there's tiny variations in the density. And so I want to make sure that the box size here is small compared to those variations. So that's the conditions which, if you like, license the use of continuum ideas. Although again, I think it's deeper than that and it's more applicable than that. But this is what you'd read in some fancy book. These ideas actually, in part, emerged from one of my, for sure, all-time scientist heroes. So many of you might recognize that as Michael Faraday. You may not know his story, but he was basically put into servitude at about age 12 or 13 in London. You can go to the bookshop. He was an apprentice to a bookbinder. And for 5 years of his life, he basically, from age 13 to 18, he worked in this bookshop binding books. And one of the things that he did is he bound the work of a chemist named Humphrey Davy. He ended up being so excited about the science that he wrote Humphrey Davy and said, I'd like to come basically be your assistant in the most trivial of ways. And he went there, and over time, he superseded his employer. He became truly one of the greatest experimentalists in the history of science. And what he did, among other things, probably many of you have done this, he took magnetic particles, iron filings, and put them on a piece of paper underneath a magnet, and then or a pair of magnets, and he looked at the so-called field lines. This inspired him to a view which was well summarized by Maxwell. Maxwell says, for instance, Faraday in his mind's eye saw lines of force traversing all space, where the mathematicians saw centers of force attracting at a distance. Faraday saw a medium where they saw nothing but distance. Faraday sought the seat of the phenomena in real actions going on in the medium. They were satisfied that they had found it in a power of action at a distance, impressed on electric fields. It's a great story. I wish I had more time to talk about it. It's absolutely riveting, the sort of way in which this notion of action at a distance arose and also was dismissed. Just in case anybody's interested, there's basically 3 pages in the Feynman Lectures on Physics, Volume 2, Section 1.4, where he tells us about Maxwell's equations in a wonderful way. Just really, really fantastic. And it all comes down to 2 things. You have vectors like electric and magnetic field. And what he does, he said, let's consider surfaces and then lines, curves. And basically, Maxwell's equations tell us things about what happens when you think about those fields on surfaces and on curves. So as I already mentioned, as far as field variables go, many of us are very used to scalar fields, the ones I show you at the top. This past week, I was down in the Mediterranean. I went swimming every day for about 50 minutes. And one of my true interests when I swim is I'm always very, very intrigued by changes in temperature. And I really have, when I'm swimming, I always detect them, but I really don't have a very good feeling for how large they are. I don't have a good sense of how sensitive we are to temperature change. But it's completely obvious. So I happen to be in Villefranche-sur-Mer, and I was swimming, a couple kilometers every day, and the temperature variation was enormous and kind of inexplicable. I'm sure it is explicable, but I didn't know what was going on. So anyway, the temperature is a very common one. The pressure is an obvious one. I just got off an airplane about 2 hours ago, and the pressure changed immensely. The very first thing I noticed when I got on the Air France plane was, if you look on the door, it says, don't open the door if there's a blinking red light because the cabin is pressurized. Okay, so we're all used to that. There are also vector fields, and those, probably the most evident one that all of us are used to is velocity. I just think about looking at a river. A river is flowing along, and then it gets thinner. The velocity field, I should be okay to fix it, I hope. Is that good? Okay, so the velocity field tells you the speed and direction of motion at different points in space. And one of the things that I'm going to be excited about today is passing back and forth between discrete and continuous descriptions. So I'm going to talk about herding and flocking and that sort of thing. And here, this sort of fantasy picture is showing you what's going on in my own mind as I go from the discrete agents, the discrete entities called birds, to a continuous field called the bird density and the bird velocity. Here, I'm going to be talking about toxoplasma, and I'm going to replace the individual discrete 100 nanometer actin filaments with density and velocity field living in the two-dimensional surface of this cell. So just a few words about what I mean by a field theory. So let's take this simple example, which is exactly one that was used by my coworker, Christina. And you have on one side of the box some chemokine. And now at t equals 0, we remove the wall and we ask ourselves the question, what's going to happen to the concentration over time? And the way that I want all of you to think about a field theory is maybe not the conventional way, but I want you to think of it as an update rule. What do I mean by that? If I want to know the concentration at position x at time t plus delta t, so think of this as concentration at a given point now, how do I get that? Well, I take the concentration before, I add up all the ways that particles could have come into position x, and I subtract all the ways they could have left. That's shown with these 4 diagrams. So here, the ith skyscraper is added onto by the I plus 1th. Here, the ith skyscraper is added onto by the I minus 1th. Here, I jumps over to I plus 1, and here I jumps over to I minus 1. That's the math of this thing. And we can solve this. So, you know, if you study physics, especially sort of more old school, traditional mathematical physics or whatever, you would solve this problem as I did using Fourier series. But I think it gives people a great sense of power, actually, to realize you don't have to necessarily learn all those analytic tools. You can just simply plug in that formula, and you will find a solution which is literally indistinguishable. And furthermore, you know, I thought I might amuse you. So this is sorry, I'm telegraphing, I'm going fast, I realize it. But this is an imitation of a one-dimensional FRAP experiment, fluorescence recovery after photobleaching. So I have a one-dimensional cell. Here, initially, we kill off the fluorescence in this region, and then we solve the diffusion equation to find out. We solve this field theory to find out what happens to the concentration over time. And in the long time limit, it becomes uniform. What I'm showing you here, the red dots, this is really to try to make a big point. Sometimes people think, oh, but that's not the way that I understand the problem. I don't think of it in terms of partial differential equations. I think about molecular hopping. Cool. It's nice to view things in more than one way. And the red dots are doing this problem strictly as coin flips, strictly as stochastic simulation. And you know, the answers are the same, and they need to be the same, because you're talking about the same thing. And that's what's fascinating, in a way, about these differences of perspective. So what I want to do now is I want to talk about wildebeest. So I'm going to spend the next 10 minutes just giving you a bit of an introduction to wildebeest and their herding behavior, and then how one might go about writing a field theory of wildebeest herds. So let me just say that it was only in the late 1950s that we as humans came to truly know that there was a wildebeest migration with sort of an annual time scale. In the early 1900s, Western hunters would go to Africa. They'd go to the Serengeti with the intent of killing male lions that had the biggest and darkest manes. Okay? I mean, one of the things to consider as you think about human impacts is that in general, out in the world of predation, it's usually the weakest that are hunted. But when we are the ones doing the predating, we're going after the strongest. It's just a thought. So it turns out in the 1950s, people started taking a careful census, and in particular, this father and son pair. They're 2 German guys, Bernard and Michael Grismek. I can't recommend to you highly enough. I'm not going to say much about it, but the stories of both of them are amazing in so many different ways. Just as one little side story, the father, at the end of World War II, he's the guy who saved all the animals in the Frankfurt Zoo. I don't know. That may sound weird to you, but I would be, as an American, we have this expression. We call certain people crazy dog person. Like, you're a crazy dog person. And that should indicate something to you. The Paris version of that is the person that shows up at the restaurant with their dog in a stroller. That's a crazy dog person. So anyway, I'm very sympathetic to somebody at the end of World War II who's worried about the animals in the Frankfurt Zoo. This father and son, they made a very nice documentary together. They wrote a book together. At age 24, his son was doing transects, counting the wildebeest. He crashed into a vulture and died. He already had 2 kids, and I'm not going to tell you much about that, but it's a story of my heart. But I want you to notice what I'm showing in the plot. Check it out. It's the population, okay, of wildebeest as a function of time. And it's very interesting. And here is the fraction of wildebeest that have antibodies against the Rinderpest virus. It turns out the Rinderpest virus is one of the great pandemics of the last 150 years. Cows were brought to Africa, to East Africa from India, and they, in retrospect, we know what happened. They had rinderpest. They basically infected the wildebeest, and 95% of the cows died. What's amusing, it's very typical, I've tried to make this point during this course, our imaginations, all of us, are limited. This past week I've been reading a book about Maxwell, and it was just fun and interesting to see the confusion even he had about the nature of the electric field and vortices, and he thought about the ether, and he was confused. That's fine. So the hypothesis was the wildebeest made the cows sick. What do you think happened in the late 1950s that led to this graph? Anybody want to take a guess? It's certainly relevant to this very day. Vaccination. So they vaccinated the humans? Toma, I'm sorry. Yeah, they vaccinated the cows. And guess what? The wildebeest stopped dying. And the wildebeest also stopped having antibodies against rinderpest virus. So at any rate, this population has been stable at this value for about 40 years now. So that's kind of the stable population size in the Serengeti. So what I want to do is I want to ask the question of how might we write down a theory to describe their motion. So to do so, we have to have field variables. So I've already alluded to this idea of using the density and the velocity as ways to characterize the state of the wildebeest population. What that means is that we need to work out equations. These equations have an objective. The objective is to tell us, just to answer a simple question, how does the density, how does the velocity change at every point in every instant? And again, if you are not clear on what I mean by that math, I want you to go back to your own totally normal experience with a river. I was driving through Paris the other day. My taxi driver, as we were driving along, said, "Oh, that's the most beautiful bridge in Paris." And I certainly didn't agree, by the way, I have to say. It's the really fancy bridge just when you're coming this way from the Tour Eiffel. I forgot the name. But the thing that's cool about it, for me, this is completely bizarre, this is the one that at water level, if I remember correctly, there's statues, right? And depending on the height of the river, you actually, as the river gets higher, they flow around those things and they make some weird flows. And all I'm trying to tell you is your experience is very clear. You might like to know, how fast is the water moving at different points in the river. You certainly want to know that if you're doing something like swimming somewhere, or if you're a surfer and you are worried about going somewhere where there's a rip current. You got to know, like what's the velocity? So that's what we want to do. So let me give you an example of how you might come up with a theory. Okay, I'm not going to tell you the whole thing, but here's the idea. So I'm wildebeest number 2, and I'm running along, and the question is, how do we as a group decide to hang out? Well, one way to do this is democratic. I look at the neighbor in front of me, and I take the difference between its speed and mine, and that's the arrow, which is green, called V3 minus V2. Similarly, I look at the one behind me, I take the difference, and that gives me a different arrow. Then what I do is I average them. That's being maximally democratic. I'm trying to match my speed to everybody as best I can. What's fun about that, at least I find it super fun, is that leads to the math of what's called the Laplacian. That's funny upside down triangle over there. Again, the math doesn't particularly matter, but I'm trying to tell you that in a way it's very cool and interesting that the systematic notion of querying your neighbors and asking how can I best match them leads to this idea of the Laplacian. There's no mass transport. This is kind of a specialist point, but often we're used to this arising when there's diffusion. But in this case, all that's happening, and I do this all the time when I swim with my friends, we swim sufficiently far apart that we have no hydrodynamic coupling, but we try to match each other's speed, and we swim as a blob, as a group. And sometimes I have to speed up, sometimes I have to slow down. I'm just always trying to match with them, and this is the math of that. So Toner and Tu wrote down a very beautiful theory. I'm not gonna talk about the details. I'm just gonna show you what the outcome of it. But each of these figures is just meant to show you that there's a physical interpretation, that I can think about what it is that the animals are doing. And so these 4 terms account for those things. Let me just comment, for example, on the pressure term. If you go to Biarritz and you stand on the cliff and look down at the beach, I've seen it so many times, the seagulls actually aggregate. And they aggregate in a way that they have a sort of comfortable spacing. And the point is that each of us has sort of a comfortable psychological radius, and I'm pretty sure I've already violated it with Toma. But right, and it's something, you notice it when you get in a subway. You start to feel like, gosh, that's really too close for me. So that's what this pressure term is doing. It's trying to say there's an optimal spacing. And the neighbor coupling is the one about democracy. This preferred speed is the idea that we have a natural pace. Okay, and I'm going to come back to that later in the context of molecular motors. So some of you might have seen the movie The Lion King. In The Lion King, there's a young male lion, and he has an evil uncle whose name is Scar. And Scar actually creates a wildebeest stampede in a gorge. And so what I'm going to show you now is the use of this theory in order to work out the mechanics, meaning the density and velocity, inside of the gorge. And what you see here is quite, I would say, not surprising, in the sense that at the top, you see this is in steady state now. The density is uniform. And at the bottom, what you see is almost all the wildebeest are running at the same speed. And for those of you that are aficionados of fluid mechanics, you're probably used to a different kind of flow attached to one of the worst words I'm aware of in the French language, truly impossible. Can you please say it for us, Pierre? It starts with a P. You know what it is. The flow, the parabolic flow. Thank you. So horrific. Anyway, so you're used to that, right? That's parabolic. That's not this. This thing is very different. Shoot, I didn't put the graph. But this thing, what it does is there's a boundary layer, and then all the agents are going at the same speed, and there's a second boundary layer. So we got excited about this video. I just want you to take a look at this for a minute. It's really quite beautiful. It has to do with collective motion in the, oh man, can't be true. C'est pas vrai. So the point of that video was to try and draw your attention to something you're used to in the world of fluids. I already mentioned it. If you have a flow of water and then it reaches somewhere that's thin, we're all used to, we have a concept of what's going to happen in that case. So if you look at the sheep, what I want you to notice is that as they start converging, there's a pileup, and they actually start to turn back. There's also a perturbation because you can see here there's some border collies, which I think is awesome. You know, that goes back to my sea lion and fish. That's an indenter. It's a problem of indentation. So, you know, there's all sorts of things to notice in this flow. And so we got interested in what will happen in the presence of obstacles. Again, this is a classic problem in traditional fluid mechanics. And I'll just tell you, I'll coach your expectations. If this were water, what you would expect to happen is that the water would speed up near the obstacle. My question to you before I show it to you is what's going to happen in the lower of the two examples. These are wildebeest now. And the thing I want you to remember is that with water, you can speed it up, right? And you can speed it up in a way that satisfies conservation of mass. Here you can't. And the toner 2 theory is smart enough to realize that. And so what's super cool about this is what happens is that the wildebeest hit the obstacle and they reflect off of it. This has actually been observed by Denis Barthelot, who used to be at ESPCI. You know, really, really beautiful experiments. He has ways of using like colloidal particles that drive themselves around. He put obstacles, and damn if he didn't observe them getting reflected off of an obstacle. And I can even tell you sort of the logic of this. When this distance gets to be the thickness of the boundary layer, that's when you get reflections. We actually made a phase diagram of it. Okay, so let me give you now a totally different example at a billion-fold or something different length scale, but ultimately the same theory. And so we started out over here, thinking about the bilateria, and now we're going to hop all the way over to the apicomplexum. These are the organisms that my book co-author Christina works on. And so we're going to talk about toxoplasma. This is the causative agent of toxoplasmosis. It's also, if some of you might be aware of Plasmodium. And so it has this very rich series of motions. Okay? There's circular gliding, there's helical gliding, there's twirling, and then there's this back and forth gliding that you see here. And so the thing I guess I would pose for you is if you think about eukaryotic cell motility, there's generally two modes of motility that most people would think of. One is this, swimming with flagella, such as Chlamydomonas, and the other is shape change induced crawling. This thing is basically rigid body motion. And so there's a hypothesis about how this works, and I'm going to just sketch it for you. I'm not going to go into big details about it, but there's a 25 nanometer layer thick region between the plasma membrane and this intermembrane complex. Now I would say people know that there's myosin motors that are anchored here, and what they do is they translocate the actin. The actin now and then gets stuck onto these adhesion complexes, and that propels the cell forward. Okay. So just as a reminder, some of you might know about this category of single molecule experiments known as gliding assays. It's one of the examples I think I've mentioned in this course, my love for what I like to call experiments to change your life for. These are the kinds of things where I go to some lab, I visit, and then on the plane on the way home, I think to myself, why am I working on what I'm working on? I should be working on that incredibly cool thing that I just heard about. And so in the world of single molecule biophysics, for sure, this is one of the categories of experiments that kind of just blew me away, that people could pull this off. So what you do is you decorate the cover slip of a microscope cover slip with the motors, which are shown there, and then you put in fluorescently labeled filaments, such as actin filaments, and you watch them glide. And at sufficiently high densities, the gliding is organized. At low densities, they go sort of randomly. And so, kind of inspired by Thomas, he has a really nice lecture in the Collège de France series where he talks about the difference between templating and self-organization. And some people had thought that these follicular microtubules were responsible for the ordering of the actin, but a totally different idea would be that they self-organize, and I'm going to just comment on that. So now let's go back to this toner and two theory. So the idea is we're going to think now about the density of actin filaments, which are moving in this 25 nanometer thick layer, and we're also going to characterize their velocities with this vector field V. So once again, we have conservation of mass. I'm not going to bore you with where this comes from, but it is exactly what you would think of. It's just accounting. The number of people, the change in the number of people in this room in the next 5 seconds is equal to how many so what we would do is we would take the number who come in and subtract the number who go out. And that's how we would figure out the rate of change of people in the room. It's accounting. It's not complicated. It's just that, just all of us, we have ways of doing shorthand. And just like in biology, there's all sorts of names that you'll encounter in a laboratory. In math, we use certain notation that can be annoying, but also extremely powerful. So I'm going to just show you the equations. They're essentially the ones that I wrote earlier. So what are they saying? I want to find out how these arrows are changing in time. I want to know how are the actin filaments aligned. And so this is telling me the rate of change of the velocity. This piece is saying, well, myosin walks at a certain characteristic speed. And if you get off of that speed, you'll come back to it. So that's what that term does. This is the term that says I want to be aligned like my neighbors. That can be mediated by proteins which cross-link them, but also by excluded volume forces. This prevents unphysical densities. This is a new term that's not present for the wildebeest, and that's a term that punishes filaments that are highly curved and tries to align them in the direction of lowest curvature. So what I'm going to show you real fast is just that using the finite element method in a way that's very, very tricky. Okay? The reason it's tricky is because it's on a curved surface. So in other words, doing the stuff like the Laplace and all that's not exactly your everyday Cartesian stuff that you'd look up on Wikipedia. You have to do some extra work. I'm not going to tell you about that, but it was joyous for us to do that. So what I am showing you is the result of the toner 2 theory. So what you're seeing, let me say it in this way, is herds of actin. This is herds of actin filaments on the surface of the toxoplasma cell, and it's something that Christina actually observed when she stabilized the actin filaments. So we call this the narwhal. You might remember a narwhal is a cetacean that has a big, I forgot what it's called, but like a horn. It does make me just feel a little bit more sympathetic. I don't know how many of you have looked at Linnaeus's original work, but in it he has a class called Paradoxa. And in there is stuff like unicorns. And I don't know, living 300 years ago, if you knew there was such a thing as narwhals, and you knew there was such a thing as rhinoceroses, I don't know, I wouldn't be that worked up if somebody told me there's such a thing as a unicorn. I'm kind of disappointed, to be honest. Okay, so now, what I just told you about did not take account of the fact that the actin can be depolymerized. Nor did it take account of the fact that the actin tends to be polymerized up at the top on this cap. And so in this case, if you include that effect, what you find is a steady state distribution, which is no longer doing orbits. It's a steady state just going towards the back end, and it's even relatively easy to see how this happens because there's 2 time scales of interest. One of them is the time scale it takes for a filament to get from the top to the bottom. And I need to compare that to 1 over gamma, which is the depolymerization rate. That's another time scale. So I'm comparing those 2 time scales. So the upshot of all this, and then basically I'm going to turn to my last part of my talk, is that we hypothesize that these actin motions on the surface of the cell are able to explain the observed distinct motions seen by this particular organism. Okay, so I'm going to spend the next 15 minutes just giving you a few summarizing thoughts. I don't know if this is a good idea or a bad idea, but it's too late, so here I go. So first of all, the whole idea of this course, I don't know how to give a 4-hour-long course, but I just basically just did. And my problem is that I love being taken on a tour. I love it. I think it's awesome. In fact, I got one this morning. I told my driver who drove me from Villefranche to Marseille, I said, dude, you got to tell me about this region. I want you to show me cool stuff. I got way more than I was asking for. It was amazing. And he told me all about, got a tour. I'm not any expert, but I learned a lot, so that was fun. So what I've tried to do is I've had this idea of, there's some cool things that have struck me as being possibly relevant for thinking about biology. Okay? I'm not a hater. I'm not against genetics or biochemistry or structural biology or development or whatever. I love all those. I love them. But I'm just saying it could be very useful to bring a quantitative mindset to the same problems because we might see things that we would not otherwise see. And so, the way I think of these lectures is that I've been here with my binoculars and just like, hey, look over there. That's kind of neat. Take a look. That's a rhino. But that's not the same as understanding how a rhino works. And so, I told you this at the beginning, but I do want to say it again. It's very important. Everything that I've talked about, I've tried to do in detail. And you can go watch it, and if you have questions, just send me a mail. So, in other words, I did not mean to imply one iota that the things I've talked about, that was like my word on the topic. This is much closer to the word that I have to say about the topics that I brought up. So what were the themes? So one is I really felt that in the spirit of Barbara McClintock, having a feeling for the organism is a great idea, and I want to have a feeling for the organism through biological numeracy. So I told you I've been swimming in Villefranche every day. I was at the hotel. This guy asked me, he said, "Il y a des méduses?" And I said, "No." And then the very next day, I decided to take off my wetsuit cap and swim, and boom, I swam right into one. It got me here and then on my elbow. But I have to say, then I got kind of interested. When I was in Portugal, I saw a bunch of Portuguese man-o-war. I've never seen those before. How do you say it again? I don't know. It's a very, very interesting organism. Sometimes their tentacles are 30 meters long, and they can be deadly. What is it? Yeah, exactly. So, so I feel like, you know, the question of a jellyfish stinging me is just full of interesting questions from a sort of quantitative perspective. How many molecules were engaged, you know? And it took me at least 24 hours before I stopped feeling it on this side. Last night I was sitting at my desk. I was in a hotel where I was in the top floor and the roofs were like this. Here's what I did on day 1. And then last night I did it right here and it still hurts. So I've been really attacking my head over the last week. Anyway, what does that have to do with anything? Just this issue of what sets the scale I think is very interesting. I told you, you know, that sometimes there are things that we think of as being quite different, and a ligand-gated ion channel and hemoglobin. And yet, when viewed through the right lens, such as the lens of the model of allostery, one concludes, oh, those are really actually the same. The third thing that I had to say had to do with the idea of beating the fate, at least temporarily, which is waiting for us with respect to the second law of thermodynamics. And then today, I wanted to give you a flavor of this idea of the world as a continuum. So now what I'm going to do is I'm going to give you 10 points. And I think of these are not from me to you, these are from me to myself. You know, my favorite parts of science for sure are the time I spend alone, 3 hours, 4 hours every morning doing calculations, or sitting in Pierre's office at a blackboard, or working with my book co-authors or my students. That's my favorite times in science. And I'm very curious about how to keep my spirit of creativity, my spirit of joy, my spirit of the mystery of the world, and not to get too wrapped up in the nonsense, of which there's a lot. And so, these are the kinds of things I think to myself when I'm just trying to remember, oh, you gotta just keep in mind your good luck. So why physical biology? You know, why did I want to talk about this stuff? So one of the things is that I think that the mindset that I tried to show you really helps us sharpen our thinking. And I love this quote from James Black. He says, models in analytical pharmacology are not meant to be descriptions, pathetic descriptions of nature. They're designed to be accurate descriptions of our pathetic thinking about nature. And I think you could, you know, you might laugh at that, and you might be a little judgmental the first time you see it, but if you actually stop and think about it, you'll say, yeah, I think that's really sensible. The way my buddy Yane likes to say it is, look, at the beginning, I tell you my assumptions. I tell you what they are. I nakedly tell you what they are. Then I do the math. You can't criticize the math part. I'm just following the assumptions to see where they lead. And it's just very interesting. Like, you can draw. The problem is it's easy to draw cartoons. I do it all the time. I mean, we've made more than 2,000 cartoons for our books with the guy who did all these figures. It's super easy. You go there and you have a fantasy and you tell it, and then you do it well, like some of the ones I've shown you, and now you think it's real. But it's just a fantasy in my mind. So I got to prove it. So I got to turn that fantasy into some math with some sharp conclusions that are testable. And what I want is to have knobs that I can tune. The next thing I wanted to say has to do with this quote from Poincaré, which I've always loved. I think it's a very important point. So what does Poincaré have to say? He says, a science is built up of facts as a house is built up of bricks. But a mere accumulation of facts is no more a science than a pile of bricks is a house. I think that's rock solid, okay? And so I think that, you know, one of the ways that you can kind of get a feeling for how we're all thinking is by looking at the way we behave, meaning people in my age group, on search committees, or alternatively when we give out fellowships and stuff like that. And we are in the moment where machine learning and big data and more data and data ad infinitum seems to be the watchword of the moment. And, you know, I'm just saying that I agree with Poincaré. It's just worthy of consideration. The next thing I wanted to comment on is what I like to call the difference between figure 1 theory and figure 7 theory. So what do I mean by figure 7 theory? For figure 7, what I imagine is, you know, you've spent 3 years doing experiments, You have some beautiful data, you write your paper, and then at the end, you have some little paragraph or two where you have a model. You say, we have a model. And then you might say the model fits the data. That's figure 7. It's retrospective. It's an afterthought almost. Now, sometimes it's really, really awesome. For example, in the case of hemoglobin. So this is from, I already showed this a few lectures ago. This is the work of Niels Bohr's father, Christian. It's the binding curves for hemoglobin. What's shown is the degree to which these 4 sites are occupied as a function of the oxygen partial pressure. These are different data sets. Note CO2, BPG, different pHs. All of these can fall within one framework and a minimal parameter set. It's very convincing. It only happened within the last 10 years, to my satisfaction. We're each allowed to be judged in our own court. And so this is very retrospective on data that was already around. But a very different idea is shown here. So this famous paper from the late 1950s by Asakura and Osawa is where the idea of what are called excluded volume forces was introduced. Let me explain what that means very simply. Let's say you have this green protein, and you have a bunch of these yellow solute molecules around. If this thing goes towards the surface, it gives the yellow guys more places to jiggle and have more entropy. So the entropy is increased if that goes there. So there's an entropic force. And I love this. Direct experimental proof of the reality of the force derived here has not yet been obtained. It's a badge of honor. It's not a badge of shame. I'm sorry, again, each of us gets to be judged in our own court. When I hear the words from a referee, to me or to somebody else, oh, there's no data, they're judging, but I'm judging right back. I'm just saying, nope, you don't understand the role of theory. The role of theory is to be ahead, to suggest new experiments. And what I will tell you is it took a long time. This is 1958. That curve is from the group of Yode at Penn, University of Pennsylvania. And we're talking like 30 years later before they really nailed it. The bottom one is from Seth Freyden. So, it takes time. The next thing I wanted to say has to do with something super interesting. And I urge all of us to think about this in the context of biology. So Joe Keller wrote this great paper. And in it, he talked about the probability of getting a heads. And he was thinking about the following hidden variable. If I take a coin, I don't have one. Thanks. Okay. If I take a coin and I throw it up in the air at velocity v0, I already know how long the trip is going to take. 2 times v0 over g. It takes v0 over g to go up and another v0 over g to come down. If I know the angular frequency omega, that means I know how many times it turned. And that's what the red and the blue bands are. It's deterministic. And what I think is absolutely hilarious in this case is that little device was built by a very, very famous mathematician named Percy Diaconis, who's at Stanford. He was so excited about this, as my interpretation of it, he decided to do the experiment. And basically, you have a deterministic coin flipper. So there's a hidden variable. Like if you happen to watch a movie of it, like that, you'd have no idea whether it was going to be a heads or a tails. You'd just be like, it's a coin flip. We're all used to that. Heads, tails, who knows? But if you use that machine and you happen to know the V0 and you know the initial angular frequency, you know what's going on. There's a hidden variable. And I always like to think of it as, if I know it and you don't, and we're going to play betting games, I'm going to win. I'm going to fleece you. I'm going to walk home with all the money if we play a betting game, because I know about the hidden variable and you don't. So the thing I want to say is that this kind of thing exists in the biological setting. I'm not going to talk about the details of this, but this is just to point out. And I think I showed this the other day in the context of the MWC model. This is 10 or 15 years worth of effort in my lab, and this is not a fit. It just comes down to knowing what the right variable is, the variable that the system cares about, not the variable that I care about when I'm pipetting. So I think this notion of hidden variables is very, very important. Okay. This may seem way off in outer space, but I think it's not. And again, I'm urging myself. Again, I'm not talking to all of you. This is my best self talking to myself about what I want out of biology, what I want to teach when I meet a bunch of 18-year-olds who are not excited about biology. They've been brainwashed and ruined by high school biology where they colored mitochondria. I have a very dear friend, I'm not going to tell you who sent me a text one night. He knows him very well too, of his kid, literally, because I always make this joke about coloring mitochondria. His kid was coloring mitochondria. He had a picture of a cell and he was coloring the organelles and memorizing. It's just like mindless. And so the point here was I'm overwhelmed by this theorem from Newton, and it's called, go look it up. They're called the superb theorems. If you look up superb theorems, Newton, this is what you'll find. So what did he say? He had to prove to himself that he could treat the Earth as a point. It's pretty shocking when you stop and think about it. When I drop this thing, it behaves as all the mass of the Earth is at the center. How could that be? How could that work? This piece of mass right here and the piece on the other side of the Earth, they attract it with a different strength because of the 1 over r squared. But if you add up all the little pieces, it still acts like it's all at the center, as long as it's spherically symmetric, okay? That's what he proved. So it's indeed superb, and the question is, how many such examples are waiting for us? I already mentioned this earlier today, but I just want to say it again, this notion of emergence, that we can always ask ourselves, am I necessarily looking at the best scale for the question of interest that I'm interested in? And then I guess I wanted to say something about the idea of a language whose characters are triangles. So when Galileo first started doing these experiments on falling bodies and inclined planes, he discovered something fascinating to him. He found that the distance fallen in successive intervals went like the odd integers. First it falls 1 foot, then it falls 3 in the next increment, then it falls 5. He knew that the sum of the first n odd integers is n squared. So he basically discovered this formula, which, if you're like me, is mind-numbingly dull. You learn it in some high school class and you're just like, why are they telling me about this? Just got no interest somehow. And yet, he was so inspired by this, he says, the universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures. And I just think it's fun. I may have mentioned this, I don't remember anymore, but I think I did, this amazing figure from Newton where he unified Galileo, who was talking about projectiles, and Kepler, who was talking about elliptical orbits. And in particular, he proved the proposition from Kepler that equal areas are swept out in equal times. Let me exaggerate the orbit of the Earth. So let's make a very, very large ellipse like this with the sun here. The point is that this is, let's call this 1 month, and this 1 month. The Earth is moving much faster here than there, but equal areas are swept out in a month. That means this area and that area are the same. Okay, so what? Well, what's cool is that Newton proved that. That's from Newton's book, the picture on the right-hand side. That's literally from his book. And all he did, all with quotes, was prove that the blue triangle is equal to the green triangle, and then that the blue triangle is equal to the pink triangle, and that's it. That proves that equal areas are swept in equal times. And then he did a last little tiny piece of argumentation at the end, which is said, let me let the edge of the triangle go to 0. That's like the calculus moment where he took a limit. So that's really beautiful. I urge you all to take a look at this paper by Wigner on the unreasonable effectiveness of mathematics in the natural sciences. Wigner was a great physicist, and this article has a really nice ending, which I want to read to you. So on the last page, here's what he has to say. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And I guess I just wanted to say, I've had lots of personal opinions that I've offered you. I don't think anybody would question the idea that it's had an unreasonable effectiveness in physics. And frankly, I think that ship has already set sail in biology too. It's unreasonably effective there too. It's just maybe people haven't caught up with that. Part of the fun that I told you a little bit about today is this playful way and useful way that we're constantly passing back and forth between discrete and continuous and discrete again. Here, I have individual molecular agents. Now I pretend that they're smeared out in some field, and then when I want to solve the theory, I go back to discrete again, but now these are not molecular elements, but they're the elements of a finite element mesh. But I'm happily passing back and forth between these fantasies, and they're very potent and allow us to make predictions. I think I'll skip that. But this one I think is very important. So I've wanted to argue that idealization, abstraction, simplification, that they are the height of sophistication. They are not a measure of naivete. And I want to use this story from Borges to make the point. So this is a short story from Borges, and that's the whole story, so I'm going to read it to you. In that empire, the art of cartography attained such perfection that the map of a single province occupied the entirety of a city, and the map of the empire the entirety of a province. In time, those unconscionable maps no longer satisfied, and the Cartographers' Guild struck a map of the empire whose size was that of the empire, and which coincided point for point with it. I want to make sure everyone understands this. He made a map that's the size of the place. That's not a good idea. Can you imagine like the Paris subway map? You unfold it, and what you get is Paris, and then you look at the map? That's completely useless. The following generations, who were not so fond of the study of cartography as their forebears had been, saw that that vast map was useless, and not without some pitilessness was it that they delivered it up to the inclemencies of sun and winters. In the deserts of the West, still today, there are tattered ruins of that map inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. And I just wanted to say, the reason I showed this map in particular is I've lived what I'm about to tell you. My two favorite places in France happen to be down here and over there. And this map tells you what I have to do to go between those two places. The fact that it misrepresents Bretagne, I don't know. Maybe that's okay. Depends on what you're trying to say. So my final point was just this idea. I wanted to leave you with this idea of digging deeper into factual versus conceptual knowledge. I mentioned to you already that there's many, many interesting factual things that we've learned, but models such as the Monod-Weinman-Schonje model, the MWC model, they give us a conceptual framework which, to my mind, transcends the facts. Again, I'm not telling you need to agree with me. I'm telling you my perspective on this matter. So I think that's also very important. So that's basically what I had to say in this course. I really thank you for your willingness to listen to me. It's, I think, most important that I acknowledge these 6 people that I have spent so much time working with on this stuff. So on the left is Ron Milo, with whom I wrote the book Cell Biology by the Numbers, and that's from our cover. And then on the left, you see Yannick Kondev and Nigel, the guy sitting down. He's the one who does all the art for all the books, including for these talks. Julie Theriault, Hernan Garcia, and Christina Heshin. And then also Thomas and Wallace Marshall. It's been a huge privilege, and I've learned so much. And then I wanted to say for this particular talk, this is primarily the work of Christina, which she did in the laboratory of Alex Dunn in collaboration with John Boothroyd and Liav Segev-Zarko. And yeah, I mean, I think those are the key points that I wanted to make. And I'm happy to entertain questions. And so, yeah, I'm sorry it's a bummer for those of you that didn't know it was going to start at 4.